Global climate change refers to the accelerated warming of the world's climate over the past 50 to 60 years attributable to the burning of fossil fuels. Since the dawn of the industrial age, developed human societies have been burning coal, natural gas, and petroleum, ostensibly to power industry, urban development, and transportation. The excessive pumping of carbon dioxide into the atmosphere is threatening to upset the delicate balance of nature. More carbon is now entering the atmosphere that can be removed through photosynthesis and other natural means. The most widely recognized indicator of global climate change is the atmospheric concentration of carbon dioxide measured at the Mauna Loa Observatory in Hawaii. Figure 1 shows the complete record to date, which spans the period from March 1958 to March 2019. The red curve shows the seasonal variations, while the black curve shows the average annual trend. This curve is referred to as the Keeling curve, in honor of Charles David Keeling, who started the record. It is clear from the record that the concentration of carbon dioxide, which was around 318 in 1958, has now, in March 2019, reached 410 ppm, all the while showing a definitely upward trend. These numbers show that the concentration of carbon dioxide has increased about 29% in the past 60 years of record. Most scientists believe that the rise in the Keeling curve is due to the excessive burning of fossil fuels, which, once in the atmosphere, tend to accumulate, since there is no natural way of returning to the Earth in the quantities in which it is being burned. In effect, the atmosphere is seen to be acting as a convenient dump for the excess carbon. How does the atmospheric concentration of carbon dioxide affect global climate change? In other words, how does an increase in atmospheric CO2 produce global warming? To answer this question, we need to look at the constituents of the atmosphere. A. Nitrogen, 78%. B. Oxygen, 21%. C. Water vapor, 0.4%. D. Carbon dioxide, 0.04%. And E. Smaller percentages of other gases. While the constituents of the atmosphere are subject to change in geologic time, they tend to be essentially constant when viewed in the time scale of human interest, say 100 years. The exception is carbon dioxide, which has increased about 29% in the past 60 years. In 1896, Svante Arrhenius published a paper entitled On the Influence of Carbonic Acid in the Air upon the Temperature of the Ground, where he pioneered the science of global warming. He reasoned that the air retains heat in two ways. One, by diffusion, as the heat passes through the air, and two, by selective absorption, since some atmospheric constituents absorb great quantities of heat. Nitrogen and oxygen, the atmosphere's primary constituents, are homonuclear diatomic molecules, too tightly bound together to be able to absorb heat through vibration. The selective absorption of heat is accomplished by carbon dioxide and water vapor, two non-diatomic molecules which are present in the air in small quantities. These two molecules consist of two elements and more than two atoms, bound together loosely enough to be able to vibrate somewhat with the absorption of infrared radiation. Eventually, the vibrating molecule will emit the radiation again, and it will likely be absorbed by yet another molecule. This absorption-emission-absorption cycle serves to keep part of the heat near the Earth's surface, insulating the latter from the cold of outer space. Other heat-absorbing non-diatomic compounds, such as methane and nitrous oxide, are also present in the atmosphere, albeit at much smaller concentrations. Of the two more important non-diatomic constituents of the atmosphere, water vapor and carbon dioxide, Only the latter has a clear anthropogenic origin. Water vapor varies in the atmosphere in largely unpredictable ways, with no direct human influence in the timescale of analysis. The selective absorption of heat through vibration by the non-diatomic components of the atmosphere effectively means that these serve as a blanket to retain heat near the Earth's ground surface, impeding its diffusion into stellar space. Their concentration is an indication of the thickness of the blanket. Thus, a carbon dioxide concentration of 410 ppm ought to be about 29% more effective in retaining heat than a concentration of 318 ppm. That this is indeed the case is demonstrated by the record of global land-ocean temperatures shown in Figure 3. This figure shows global surface temperature anomalies, the black squares, and their 5-year running means, the red curve, using a base period of 1950 to 1980. The data indicates that global surface temperatures have increased about 0.6 degrees Celsius since 1960. Thus, there is very good reason to believe that Figure 2 is the cause and Figure 3 the effect, and that the Earth's surface air temperatures are increasing. Since the burning of fossil fuels is the only process that can pump carbon dioxide to the atmosphere in such great quantities, it is readily seen how this activity, which has taken place in earnest in the past 50 years, may be regarded as the culprit. The effect that protracted global warming will have on the global hydrologic cycle, on the weather and climate, and on the world's ice caps and glaciers is now beginning to be examined. Here we focus on the White Range of Peru, which features the largest concentration of glaciers in the tropics. It is clear that global warming is bound to significantly affect these glaciers. The White Range of Peru is located between 8 degrees 23 minutes and 10 degrees 2 minutes south latitude, encompassing 122 mountain peaks with elevations above 5,000 meters, of which 15 of them lie about 6,000 meters. In 1970, the areal extent of the glaciers was measured at 723 square kilometers, which comprised 26% of the area covered by all tropical glaciers. There are 755 glaciers in the White Range. As it is usual in the tropics, these glaciers are small in areal extent, averaging 1 square kilometer, with only 12 of them exceeding 5 square kilometers. This figure shows the salient geographical features of the White Range. A. The outline of the basin of the Rio Santa, or Santa River. B. The location of the snow-capped White Range along the eastern boundary. And C. The snow-free Black Range along the western boundary. The following are noted. 1. Principal mountain peaks above 6,000 meters elevation. 2. Cities in the vicinity: Caraz, Yungay, Huaraz, and Recuay. 3. Meteorological station at Querococha. 4. Glaciers Brogy, Uruas Raju, and Yanamare. And 5. Lakes with risk of avalanche. The effect of global climate change on the health of tropical glaciers is predictable. There is and will continue to be glacier melt, which, depending on the extent of the recession, may partially or totally compromise glacier integrity. The glaciers of the White Range are large compared to other glaciers of the tropics, and therefore are likely to last longer. Smaller glaciers in Venezuela, Colombia, and Ecuador are either in frank recession or have already disappeared completely. The effects of global climate change on the White Range of Peru have been documented since the late 1960s. Measurements on the Brogy, Uruas Raju, and Yanamare glaciers are shown in Table 2. pointing to increasing recession rates since 1982. Moreover, recent studies of the Yanamare Glacier have shown that the average recession rate in the 6-year period from 2003 to 2009 has exceeded 30 meters per year. Based on current recession rates, researchers have projected that the Yanamare Glacier will disappear within 50 years. This figure shows Lake Querococha, located west and downstream of the Yanamare Glacier, with the glacier visible in the background. The figure, taken in 2003, shows that at that time the glacier may have been much greater. The effects of global climate change on the White Range and other glaciers of the tropical zone are not limited to glacier recession. The effects encompass a gamut of related changes in different fields, including A. Climatology, B. Geomorphology, C. Hydrology, D. Ecology, and E. Socioeconomics. These changes are described in Table 3. Changes in the White Range are currently occurring and are expected to continue well into the future. Glacier coverage has declined by more than 25% since 1970. Furthermore, between 1951 and 1999, average temperature has increased 0.35 to 0.39 degrees per decade, significantly at an accelerating pace. Glacial lakes develop as a direct result of glacier melt. Large glacial lakes, particularly those with more than 5 million cubic meters of water, pose significant risks for local residents and infrastructure, in view of the scale of the destruction that would ensue from an outburst flood. In 1953, a comprehensive glacial lake inventory revealed the existence of 223 lakes in the White Range. 35 of the 223 lakes were classified as unstable, with 23 of them requiring immediate attention. With protracted global climate change and the rise in average temperatures, the number of glacial lakes in the White Range has continued to increase. In 1962, a second inventory resulted in a total of 263 lakes. By 1997, the number of lakes had increased to 374. Presently, the number of glacial lakes in the White Range is more than 800. Figure 8 shows the Nevado Volcan near Carhuaz, a typical example of a glacier featuring many glacial lakes. The growing role of melt during the dry season may be surmised. Overall, runoff has 3 sources. 1. Melting of glaciers. 2. Direct runoff, which comes from precipitation. And 3. Base flow. In the White Range, researchers have reported significant differences between the composition of the average annual runoff and that corresponding to the dry season. For example, in Lake Querococha, data indicates that during the dry season, melt volume is half the runoff volume, while the average annual volume of melt is only a quarter. The glaciers of the White Range have sustained the population of the upper Santa River for millennia. The entire region is referred to locally as the Callejón de Huaylas or Huaylas Corridor, due to its elongated shape along the river, flanked by the White Range to the east and the Black Range to the west. The population, consisting of about 320,000 people, is distributed among hundreds of small rural settlements, with approximately half of the people living in major urban clusters along the Santa River, including the cities of Huaraz, Yungay, Caraz, and Recuay. Huaraz, a major urban center with about 120,000 people, is the capital of the department of Ancash. The danger of glacial lake outburst floods and avalanches remains a threat in the White Range and very likely to be exacerbated by continuing global climate change. Table 6 documents the most important glacial lake outburst floods of the past 75 years. A total of 29 have been documented since the year 1725, with the majority of them occurring in the past century alone. The cities affected have been Huaraz, Chavín de Huántar, Huallanca, and Caraz. Global climate change, specifically anthropogenic global warming, threatens to upset the delicate balance of nature, wherein the global climate is determined by the concentration of non-diatomic gases in the atmosphere, among them, significantly, carbon dioxide. The sustained warming of the past 50 years has produced a host of negative effects. Here, we highlight the effect that global warming has had on the tropical glaciers, including melting, recession, and their possible eventual disappearance. This places in jeopardy the continuance of a wide array of natural services, among them the supply of water resources, the conservation of flora and fauna, the aesthetics of the natural landscape, and the societal activities of tourism, mountaineering, and alpinism. We specifically focus on the White Range of Peru, a resource of global importance and significant aesthetic value. Life of all kinds stands to be negatively affected by protracted global warming and the impairment of the White Range. The following conclusions are drawn. The concentration of carbon dioxide in the atmosphere has reached 410 ppm at the present time, March 2019. The increase has been mostly attributed to the excessive burning of fossil fuels. Global average surface temperatures have increased about 0.6 degrees Celsius in the past 50 years. The rise in global surface temperatures has negatively affected the tropical glaciers, causing a decrease in aerial coverage. The changes have been gradual, but the rate of change appears to be increasing. Average rates of glacier recession over the period 1930 to 2009 have been measured at 0.62% per year, and over the period 1990 to 2009 at 0.81% per year. A recent official study has documented that the loss of glacier area in the White Range in the period 1970 to 2003 has been 27%. The lakes have nearly doubled in number over the past 60 years, from 223 at the time of the first inventory in 1953 to more than 800 at the present time. Continuing glacier melting poses a significant threat of glacial lake outburst floods. The latter consists of water, snow, ice, and debris. If not adequately controlled, these disastrous events will spell havoc and destruction in the communities located directly in the path of the floods. Urban relocation, although a sensible decision in the eyes of many, remains politically difficult. Many of these devastating floods have occurred in the White Range in the past 100 years, and the chances are that they will continue to recur. Relevant scientific understanding, coupled with enlightened interdisciplinary management, is necessary for the national government of Peru and its partners in the international community to develop an effective strategy to cope with these threats. Sustainability being clearly out of the question, the aim remains to mitigate and reduce the effects of global warming within the next 1 to 2 generations.